Alright guys, so this is going to be the second video that we have for the spreadsheet side of things for this extra credit project. In the first video we've learned how to code in our formulas for our reactions and for our internal forces, and now we need to code in our formulas for our section properties and our stresses, right? And we just did the hand calculations to figure up what our formulas for our moment of inertia and our Q should be as well. So let's just go ahead and take those equations that we determined from our hand calcs and just type them into our Excel sheet. All right. So for moment of inertia, we said that the moment of inertia of the cross section was the BH cubed over 12 terms for the overall out of the shape, and then we subtract out the negative space, so that was equal to, we say is equal to B sub F times D cubed over 12. So we come up here, we say B sub F, and we'll say times D cubed over 12, and then we subtract out the negative space, the width of the negative space being B sub F minus T sub W, so we say B sub F minus T sub W. Alright, we gotta multiply that times the depth of the negative space, which is D minus 2 T sub F. So we're going to put parentheses. We're going to say D minus 2 times T sub F. That's the depth of the negative space, and then that gets cubed, and then we divide that by 12. And I believe that should make my formula work out just fine. And it does, comes out to 199.9, which if you take a look at the validation sheet, that's what we should have got. Okay. Same thing. We are now just going to enter in our formula for the Q of this cross section. Again, we've already figured this out by hand, so we know that our formula is B sub F times D sub F. B sub F times T sub F. That's the area of that top flange. And then we're going to say times D over 2 minus T sub F over 2. Okay, so that's A and Y bar prime for the first shape, and then we add in A and Y bar prime for the second shape. Area of the second shape is D over 2 minus T sub F. D over 2 minus T sub F. Then we take that and we multiply by T sub W. And we take that and multiply that by half of D over 2 minus T sub F. Okay. And that should have the equation right. Let's check it real quick. We get 16.1, and that's what it was supposed to be. Perfect. So now that we've entered in our equations for moment of inertia and for Q, now we can just come down here to our stress section and type in our formulas for shear stress and bending stress. We know the formulas for shear stress and bending stress: tau equals VQ over IT, and sigma equals MC over I. So we're just going to enter those formulas in here. So for the shear stress, we're going to say is equal to V, which is the shear at the location. that number, times Q. We just say times Q. And then we're going to divide by I times T. So he's going to say I times T, which for our maximum shear stress, right? The maximum shear stress occurs at the neutral axis. So the width of the cross section at the neutral axis is just T sub W. So we come back up here and we choose T sub W, close out the parentheses, click enter, and we should get 1005.7 psi, which is what we should have got per the validation. All right, same thing for max bending stress. We just take the moment times C divided by I. So we'll say equals the moment is this number here, but pay attention to our units here. That number is in foot-pounds, and our C and I will be in inches. So I'm going to go ahead and multiply by 12 right here to put that in inch-pounds. Okay, so that's M. Then we need to multiply by C. And keep in mind that the maximum bending stress occurs at the top and bottom of the beam cross section, correct? So our C is actually just equal to D over 2. So we say times, and we'll say D over 2. All right. So that's M times C, and then we just need to divide by I. So we just say divide by I, and click enter, and we get 2,959.4 psi, which is what we should have got. If you want to check yourself again, we can go back to our second point of validation. I give you 2 points of validation for every beam, just so you make sure you're right at both values, right? So now we'll go to a location x equals 12. Our shear and moment are still correct. Moment of inertia and Q do not change because those are section properties. Doesn't matter where they're at along the beam. And then our max shear stress is negative 279.4 and 3014.2, which per the validation is what it should have been. All right. So this is it. This is what I'm looking for. This is the spreadsheet that I'm looking for. This is how I want it to be filled out. And this is everything you need to do. So you come in here, you can change up these parameters to be anything you want to be. You can get any kind of load, any length of beam, put the load anywhere on the beam, and then you can come in here with any generic symmetric I-beam, type these values in, and then you can calculate what your reactions and internal forces and stresses are. All right. So this is problem 1. Everybody should at least get this problem 1 done. Beams 2 and 3 are going to be up to you guys to code in all the formulas that you develop from your hand calcs that you need to do. All right. I think I said it in the last video, but I'll just repeat myself real quick. This will be due sometime. You can turn this in anytime before the final exam. The whole thing will be worth 30 test points, each beam worth 10 points. So if you only do beams 1, 2, 1 and 2, you'll get 20 points, right? But at this point, everybody should get at least beam 1 because we have done beam 1 pretty much completely together. All right, so should have at least 10 bonus points right here. All right, well, I think that's everything I need to say, so I'll stop rambling and let you guys get to work on this thing.